Hey, good morning. Hope everyone's doing well. Let's get started. So we had been talking about isotopes last time, right? And an isotope is the same element, but it has the different number of neutrons. If we change the neutrons, think about what are the properties of a neutron. They have mass, but they don't have a charge. So if we change the number of neutrons, we won't change the charge of the material, but we will change its mass. So we'll make it heavier or lighter. And so we had this formula that we sort of followed where we take the mass and we multiply it by its abundance divided by 100, so get it out of percentage. And then we add each of those individual contributions together. So I want you to do this one here. So gallium has two isotopes. There's gallium-69, but it's actually 68.926. So use the more specified number if it gives that to you. And then there's gallium-71, which really has a mass of 70.925. And these are their relative percentages. So I want you to calculate the atomic mass of gallium. Okay, so I told you guys that sometimes they give you a more specified atomic mass, sometimes they don't. It just, if they don't give it to you, just go with whatever the overall number is. So you could use 69, but since they've given it to us, we're going to take this number and we're going to multiply this unpercentaged. So we need to move the decimal over 2 places in each of these situations and just multiply those 2 numbers together. And then we add each individual one up. So we've got our 68.92 for the gallium-69, and we multiply it by the 60.10 divided by 100. And its contribution, the gallium-69's contribution is 41.42 AMU. So most of it is actually coming from there. The remaining gallium is gallium-71, which is actually 70.925. We take its almost 40% divided by 100, and we get 28.30. The last step is to add these 2 things together, and we get a number close to what, 69.72, and that should be what the periodic chart has as well. Yeah, they usually do pretty close experimental values. So this number, one way to kind of confirm, this number needs to sit between this mass and this mass. If it doesn't, something went awry. And, you know, we've got 69 and 71, but a majority of it is the 69. So we expect this number to sit closer to 69 than we would 71. Like if your number came out as 70.885, you're giving too much weight to the 71 here. So you might want to recalculate. So you probably have a problem like that on your next exam. I'm comfortable with that. All right, so the last thing that we're going to talk about are electrons and electron energy levels. If you've taken chemistry before, like 092, or you just finished up high school chemistry, and you did electron configurations and electron shells where you had numbers and letters, we're going to simplify it, okay? This is going to be much easier than that. We're not going to give shapes. We're just going to do numbers, all right? So you'll just have to memorize what is the first one, how many can fit in there, how many electrons can fit in the second one and in the third one, and that's it. And I'll show you in a minute. So this is just how mastering chemistry is going to, and the tests as well, are going to want you to do electron configuration. So I'll show you. All right, here's a rainbow that forms when light passes through water droplets. The water droplets act as a prism and it spreads the light out, because white light coming from the sun actually has all of the colors of the rainbow hidden in it. And we can experience them when they move through a prism. So light is a form of electromagnetic radiation. And there are a lot of different electromagnetic radiations. The spectrum for electromagnetic radiation is much broader than just natural light. We as human beings don't have the capacity to like see with our eyes those other electromagnetic radiations. There are some animals that can see some of them or sense them. The electromagnetic spectrum is organized by like how energetic it is, what its wavelength is, and or what its frequency is. So if we're talking about the wavelength of a type of radiation, wavelength is talking about like crest to crest or trough to trough. So if I put a wave here, and I'm gonna try and make this as symmetrical as possible. Okay, so from this point to this point, we would call that one wavelength. So that would be, or sometimes it's called lambda, or it's this like little cursive-y looking H. Or a trough from here to here is also that distance, lambda. So as that becomes longer, your wavelength gets bigger. Longer wavelengths have lower energy. Okay, short wavelengths have high energy. So they're inversely related. As one goes up, the other goes down. So think about if you're sitting in like a wave pool or something, if the waves are really long, your experience is very gentle, right? You go up and then you come down and then you go up, right? Your cocktail doesn't spill. because it's low energy. If it's a short wavelength, if they've got it oscillating really fast, you're going to go up, down, up, down, up, down. There's going to be a lot more energy in that wave system. So as far as the atomic spectrum is concerned, we're just going to brush on this really quickly, but every element, when you excite it or you like burn it, it'll produce light. Barium produces a sort of greenish light. If I take that light and I pass it through a prism, it's going to show this thing called the barium light spectrum. So every barium, whether it's in the United States or India or on a different planet, if you burn barium and you spread out the light that it produces, it will always have lines at these points. So you can actually use these to identify different minerals, or rather different elements, because if I burn barium versus burning magnesium, they're going to have their own unique light spectrum. So why are there lines? Like, why does it look like this versus if we were to pass natural light through a prism, what would we get? We get a complete rainbow, right? We get every single spot filled in. Why are some of the spots missing here? It has to do with these discrete shifts in energy change of electrons. What does that mean? Okay, when I burn or excite this barium, the little electrons that are floating around the nucleus get energy and they start going, ah! And what they do is they want to jump to what's known as a higher energy orbit or orbital. You can kind of think of how the electrons sit around the nucleus as onion layers. All right, so at the center is the nucleus, and then there's these layers of onion that wrap around it. The onion layers that are farther from the nucleus are higher energy. The onion layers that are closer to the nucleus are lower energy. Why? Well, the nucleus is positive, the electrons are negative. So they want to naturally sit next to each other. They're attracted to each other. So if I'm going to pull that electron away from the nucleus, it has to have some energy to do that. So in an atom, each electron is assigned a specific energy level. And the energy levels, which are called principal quantum numbers, have this little italicized lowercase n. The lowest energy is 1, then 2, then 3, then 4, so on and so on, all the way up to 7. Again, if you've done the shells with the S and the P and the D, we're not going to do any of that. Okay, we're going to keep it super simple. All you need to know is that energy level 1 is the lowest energy. You fill that one first. Energy 2 is next, and you fill that, and so on and so on. So increase in energy as the value of N increases. So as we go, this is kind of the closest onion layer to the nucleus. This is the next one. As you go to broader onion layers, you are increasing the amount of energy. Well, that totally jumped around there. Okay, so we'll go back to this in just a second. So here are the different, we can think of the different energy levels as being quantized. That's what they call it, quantized. And what that means is that they're discrete levels. So energy level 1 is the books on the lowest shelf. Here's the nucleus, low energy. If I want to get the book onto N equals 2, it can't sit somewhere between the shelves, right? It's either got to be on this first level, or I've got to pull it out and put it onto the second level, or I got to pull it out and put it onto the third level. That is what the quantized definition means. It means it can only exist on either this one or this one or this one. You can't be like between levels or rungs. But anything that is on the same shelf has the same energy. So this book over here and this book over here are sitting at the same energy level. These 5 books up here are all sitting at the same energy level. So here's our nucleus, and we can think of this as the first onion layer, the second, the third. As we bring the books up to higher levels, they contain more energy. In this case, it would be, if the book fell from the 5th level, it's going to hurt much more than if it falls from the first level on your head. So why they put that there? well, we're just going to keep going with this because I don't want to lose track on it. So why are we getting these lines at very specific colors? Well, because what happens is that when you have an atom and it absorbs energy, like you plug it in, it's in a vacuum tube and you plug it into the wall, or you light it with a flame, the electrons get excited. So this electron that's normally on the first level here, it gets excited and it wants to go up to a higher energy. It's absorbing energy. Well, at some point, that energy is going to go to like the atom next to it, you know, and it's going to lose that direct absorption of energy. And so it's going to fall back down. All right. It's going to release back to its lower energy or its original energy state. When it falls back down, it has to release that energy. It has to give it up. So it's kind of like, you know, your child is starting to freak out and they all of us, you know, you gave them candy and they're like, ah! So they go to a higher energy level. And then to get your kid back to a lower energy level, you've got to release that energy somehow, right? So you send your kid out into the backyard or they go into their room and scream for 5 minutes. But somehow that's got to get released. Now, how do these electrons release energy? They release it through light. So at very specific points, like this one here, this electron went up and then it came down. It didn't do a very big hop. So it produced a low light energy, which is red. This one down here, this electron jumped up a couple levels. This is a bigger energy change. So when he falls back down, he's going to produce a higher energy or something that's green. So let's look at the electromagnetic spectrum to see what the ordering is. But right, do you guys see this little section right here with the visible light? If we expand that out, so we're going to stretch it out. This is low energy on this side. This is high energy on this side. Or this is long wavelengths. This is short wavelengths. So we can see red light sits on the lower energy side. Purple light sits on the higher energy side. So if an electron goes up just one level, it's going to be in this range here, right? If it goes up 2 levels, 3 levels, starts going like really high away from the center of the nucleus, it's going to produce a higher energy light. So let's I'm just going to fill in a couple things so you can rewatch it later. So we've got wavelength here, and this is large wavelength. This over here is short wavelength, right? High energy. Frequency, okay, this is a low frequency. This is a high frequency. So what are some other things that are in the electromagnetic spectrum? So we can see this. Just outside of that, let's move in this direction. This is the lower energy direction. These are things that we interact with like on a daily basis. So right next to the red, if I go just past the red, like our wavelength is just a little bit longer than the red, we move into this range called infrared, which is sort of named appropriately to be next to the red. There are animals that can, snakes and reptiles that can see, sense, and infrared. Heat lamps, satellites, things like that are working in this infrared range. If we go farther than that or longer, we go into a microwave. And yes, a microwave is included in the microwave section. Also cell phones and some television. And then the longest wavelength, we've got our radio waves, okay? These are all harmless for people. Sometimes people get a little freaked out by microwaves. Okay, they're longer than visible light. They have like less of an impact for cellular degeneration than visible light does. So you're good. Over here though, when we get into the higher energies, let's go all the way. So we've gone through these, we're in the visible light spectrum, we get to purple, and then we're just slightly shorter, higher energy than purple, we move into that thing known as ultraviolet. And ultraviolet light is what is comes off of the sun, the magnetosphere and the atmosphere, or not the magnetosphere, but the atmosphere helps to block some of this ultraviolet light. Sunscreen helps to block some of it as well. But it has an effect on biological cells. So it can give you a tan if you spend too much time out there. It can give you a sunburn if you spend repeated amounts of time. It can give you skin cancer, right? Because it's higher energy, so it can start to break down the cells. If we go even higher energy than ultraviolet, we get into X-rays. X-rays have so much energy to them that they can actually pass through the soft tissue of your body and hit against your bones so that you can get an X-ray. These are definitely more dangerous than ultraviolet, right? You don't want to be getting X-rays on a daily basis. People who perform X-rays usually stand behind a concrete wall because they don't want to be exposed to those. And then highest energy after X-rays are gamma rays. Those are what come off of the sun. They're what come off of nuclear reactions, all sorts of stuff like that. So our magnetosphere, which is this sphere outside, farther out than the atmosphere, that's formed because of the movement of magma in our core, it keeps us safe from all these gamma rays because there are gamma rays being shot off from our sun constantly, and we would not do well if we didn't have that. So as far as these numbers here, wavelength in meters, we're in the 10 to the negative 7th sort of range as far as meters, or that if 10 to the negative 7th is tiny. So you may want to go with something called a nanometer, right? Use the prefix nanometer. So the range for visible light is 700 to 400 nanometers. This is our purple light. This is our red light, okay? Red light is longer wavelength than purple light. You do want to know the electromagnetic spectrum as far as like the ordering is concerned, which ones are longer, which ones have higher energy. If I was to say, hey, what has higher energy, microwave or gamma ray? You would be able to say gamma rays, much more energy. Okay, so back to the electron thing. So electron arrangements, you are going to be doing some of these, very, very basic though. So for the period one, now period one, period is talking about row, okay? So period one is hydrogen and helium. So on your periodic chart, you might want to put a little 1 next to the row where hydrogen starts. Your electron arrangement for hydrogen, you have 1 proton, so you have 1 electron. So in the first energy level, you have 1 electron. Helium, you have 2. The first energy level can only hold 2 electrons. So after we get to helium, we have to move to the next onion layer. So if we move into the second period, which is next to lithium, you can put a 2, right? Or your periodic chart may already be numbered with those. Lithium, beryllium, boron, carbon, all those through neon, those are all in the second energy. So you always fill the lowest energy first, right? You're going to pack the electrons into the first onion layer, and then you expand to the second onion layer. So you might start to see here that you're literally just piggybacking off of the atom that came before, right? This lithium has the 2 from helium, and then it adds 1 more into the second. And as we go through period 2, we just add 1 electron. Neon, which has got an atomic number of 10, would have 10 electrons as well, 2 here and 8 here. The second energy level can hold 8 electrons. Okay. Here is energy level 3. So let's say we're going, we've already filled to neon, and now we want to do an electron configuration for sodium. Well, sodium is going to have the original 2 in the first, it's going to have a full 8 in the second, and then it's going to have 1 in the third. And you just go through that. Here are the number of electrons that can get filled in each of your energy levels. So you want to know these. So the first energy is 2, the second is 8, the third is 18. Why is it 18? Because it's including some of the transition metals. The fourth is 32, the fifth is 32. Again, why are those so large? It's because they're including the lanthanides as well. Or they're including F orbitals, which we're not going to get into for this class. Just know the filling orders. So let's look at oxygen. Find oxygen on your periodic chart. To get to oxygen, you first have to fill the top row. So that's 2 in the top row, and then you put a comma and then 6 in the second row. Calcium, number 20, you've got to fill the first 2, then you put 8, and then 8 in the next one, and then you do 2 in the following one. Now, this one holds a total of 18. The reason that we haven't gotten to that is because the transition metals, which are known, I hate how this is taught. I hate it. It's simpler, but it is like more complicated. The Ds, the transition metals, are 1 energy level lower. So when you get to scandium, titanium, on your periodic chart, 21, 22, 23, 24, those are actually going to fill this back in. I'm really only going to have you guys fill these to probably argon. Yeah, we're just going to say argon because this doesn't really help out at all for this class. So write the electron arrangement for the following. We'll do carbon together. So carbon is number 6. So in order to get to number 6, I need to put 2 in the first, and then I need to put 1, 2, 3, 4 in the second. Okay. I want you to do the other 3. If you can do these, you'll be good for the test with this funky electron configuration. Okay, so I don't want to spend too much time on these, but so for carbon, we said that there were 6, so you put 2 in the first and 4 in the second. For silicon, there's 14, so we put 2 in the first, 8 in the second, and 4 in the last. For oxygen, 2 and then 6, and then nitrogen, which is an odd number of 7, 2, and then 5. That's it. Great, we're done with that. But you do want to be comfortable with these things called periodic trends. So on your periodic chart, talk about how the atoms relate to each other. So the first thing, atomic size. I guess I don't want to wait. We'll wait a little bit. We'll wait till we get to the end. So group number and number of valence electrons. So let's first talk about what a valence electron is. A valence electron is the number of electrons that are in the outermost energy level. Why is that important? Well, think about your onion. So if I've got my nucleus in the center here, and let's say I've got, here's my first onion layer. There's an electron here and an electron here. And we said that first onion layer can only hold 2 electrons. Then we've got our second onion layer, and I've got an electron here and an electron here and an electron over here. I would say this thing has 3 valence electrons. 1, 2, 3. We don't include the guys in the center. Why? Because they're in a complete shell. They're happy, they're doing their own thing. They're not going to be involved with bonding. It's this outer layer of electrons that are that's what's going to give you bonding properties. All right. So if you look at the noble gases like neon, for instance, neon has 8 electrons in its outermost shell. That's very stable. That's known as an octet. Super stable, it isn't going to bond. That's why we don't see them bonding a whole lot. So with the main group elements, this doesn't include transition metals, but with the main group elements, the number of the row you're in is the number of valence electrons you have. So if you're in column 1, you have 1 valence electron. If you're in column 2, you have 2 valence electrons. Let's go over to where nitrogen is. Nitrogen is in column 5. It has 5 valence electrons. Fluorine, column 7, has 7 valence electrons. And then the noble gases have minus helium have 8 valence electrons. So that's different than the charge though, right? So if we look at, let's go back to nitrogen and phosphorus's column. That column has 5 valence electrons, but I told you to write a 3- above it a while ago because they like to form a -3 charged ion. So don't mix valence electrons and charge up. So group 1, 1 valence electron all the way down to group 8. You will need to do simple dot structures for just elements. If you remember from, if you remember from your previous chemistry class doing like Lewis dot structures for compounds and stuff like that, we're not going to do that stuff. You're going to keep it really basic. So when drawing what's known as an electron dot structure, you're going to put the symbol of the element, and then you're going to put these dots around it, but you only put dots for the valence electrons. You don't do all the electrons. So aluminum, which is number 13 on the periodic chart, has a total of 13 electrons. But when drawing its dot structure, we ignore any core electrons. We just want to look at what's happening on the outside because those are the guys that are going to affect our bonding. So aluminum has this situation. Gallium, Ga, also has the same Lewis structure, dot structure. It also has 3 because it's in the same column. So here are some dot structures for magnesium. Magnesium is number 12. But remember, we don't include the first electrons because those are in complete sets. They're happy, they're good. We're only going to look at the outermost electrons and the outermost energy level. There are 2 electrons. So we put 2 electrons. Do you see how they're written in sort of a variety of ways? These all mean the same thing, right? The one thing I don't want you to do is just put them next to each other on the same side. They need to be, we can think of this as side 1, 2, 3, 4. Fill in singularly. Don't double them up. So magnesium has 2 valence electrons. There they are, boop, boop. We're just looking at what's happening in the outermost shell. Here are some of the electron dot configurations for a few elements. Notice that they're very similar when they're in the same column, right? So if we go to group 4, there are 4 valence electrons. That means that when you draw carbon, you'll have 4 electrons. Or if you draw silicon, you'll have 4 electrons, or germanium, you'll have 4 electrons, because each group has a similar properties. This is why their properties are similar. Think of your electron dot. There are 4 sides. You always fill in individually, and then you go back and double up. So I don't add the second one until I've filled in at least 1 on each side. You can start to see it happen here with nitrogen. Just show you what sometimes I see students doing that will not work out for you, especially like with the homework. So I have nitrogen. This has 5 valence electrons. So I don't want to go like this, 1, 2, 3, 4, 5. Why? Because it's lopsided. This area doesn't have any electrons, and these are all negatively charged. So they want to get as far away from each other as possible. So we don't want to fill like that. Instead, we want to fill individually. So we've stretched them out and then go back and double up. The software will notice a difference between this where you have two coupled together versus this where you have one coupled together. So just make sure you're following that format. Okay, so I want you to write the electron dot for these three elements: chlorine, carbon, and nitrogen. Okay, so shouldn't take too long to do these. For this first one, chlorine. So chlorine is sitting in column 7. So that means chlorine needs to have 7 valence electrons. So I'm going to write the symbol for chlorine, and then I'm going to start filling in. I fill in 1 on each side first, and then I'm going to go back and double up. There, there, and there. So I've got a set of electrons here, a set here, a set here, and then a single one here. If your single one is sitting on the top or your single one is sitting on the bottom, that's fine. All right, it means the same thing because you can rotate the electron around in space. Carbon is in column 4. So how many valence electrons? 4, 7, 4. So 1, 2, 3, 4. Again, you wouldn't want to double up first like this. That's kind of wonky and lopsided. We want to spread the electrons out. And then nitrogen, which has 5 electrons, we're going to single it up. And then we'll go back and double it up. Pretty simple. All right. So talking about trends on the periodic chart. So we've got this idea that each column, they have similar properties. They have similar electron dot structures because the number of valence electrons they have are the same. So there's this sort of repeating pattern. Another thing we want to look at is atomic size. So the size of an atom is determined by its atomic radius. That is from the nucleus all the way out to its outermost electrons, or how far are the valence electrons sitting. The biggest atom on your periodic chart is going to be the lower left-hand corner. So if you go down to 87, where you have FR, sometimes it's called Fat Frankie, those are the biggest. So write big in that corner. Upper right-hand corner where helium is, that's going to be the smallest. All right, so put small. And then they all just sort of fill in relative to those two corners. So it increases in size from top to bottom. So every time you drop down a row, you're adding an onion layer of electrons. It decreases within a period. So as you move to the right across a row, you're actually getting smaller because the number of protons is increasing. So it's holding that onion layer closer. So here's sort of a more visualized representation of that. So biggest ones down here, smaller up here. So if I was to say, hey, sulfur and phosphorus, which one is bigger? You would say phosphorus, because it's getting closer to that corner. Which one's smaller, rubidium or gallium? That's an easy one, gallium. There's another property that we can relate to the location of the atom on the periodic chart, and that's ionization energy. And so ionization energy is the amount of energy required to remove one of the outermost electrons. So if I want to take an electron off, pop it off, like here, sodium, if I add a certain amount of ionization energy, I will form the Na plus, and I will have pried an electron off. Ionization energy, for the most part, decreases as you move down. Why does it decrease as you move down? Well, as you move down, your atom gets bigger. So those outermost, see how here the outermost electrons are really close to the nucleus? That means that that electron has a big pull, or there's a big pull from the protons. So it's hugging that electron really close. Here, these electrons are like barely holding on, right? The distance is so much larger that it's real easy to pop one of those off. So decreases as we move down. Ionization increases as we move to the right. What do the metals like to do? They like to give up electrons. They don't really want them anyway. So it does require a little bit of energy to take the electrons, but not much. These things over here, they don't want to give up their electrons. They want to eat up electrons. They want to form a negatively charged thing. So as far as ionization energy is concerned, in the upper right-hand corner by helium, put high ionization energy. And down where fat Frankie is, put low ionization energy. It's real easy to get an electron from Frankie. Let me draw, I'm going to draw the structure, this structure here. Well, actually in sodium. So sodium's dot structure looks like this. Fluorine's dot structure looks like this. All right, everything, and this is why bonding happens, and we'll get a little bit more into this, but everything wants to form like a full outer valence shell. They want to have this thing complete. And a complete outer shell for the most part, unless you're in row 1, is 8. So if I want to make this 8, taking this electron away is not moving in the right direction, right? I've gone from 7, I'm so close to having 8, and now I have 6. No, that doesn't work. Instead, it would make more sense to put an electron on there to get 8. That is why this has such a high ionization energy. Versus this thing over here, look at sodium. Sodium's got this almost empty outer shell. It just needs to get rid of this. So if it can get rid of that electron, then it has a complete outer shell from the lower onion layer. That's why it's so easy to pull that thing off. So next thing, metallic character. This should sort of feel like common sense just because where you know things are. But the most metallic thing on the periodic chart is Frankie. All right, so lower left-hand corner, very metallic. Upper right-hand corner, lowest metallic properties. It follows the prevalence of that zigzag line. So over here, very, very metal-like. We would call these things very much metals. These don't have any metallic properties. So here's a summary. Excuse me. Here's a summary of all of those properties that you want to be able to read off the periodic chart. So mark up your periodic chart so that you know all of those, because it's possible that we give you something where we say, hey, here's a bunch of atoms, arrange them in order of their metallic character, or organize them in size, or which one is easier to take an electron from, things like that. Let's do it. Okay, so we've got carbon, nitrogen, and chlorine. So find those on your periodic chart. Carbon and nitrogen are right next to each other. Chlorine is just down and to the right. Determine which one is the largest, which one has the highest ionization energy, and which one belongs to group 5A. All right, so the largest atom here will be carbon, because I know that it's a little tricky with the chlorine, but carbon is sitting, a couple steps closer to where Frankie is. The highest ionization energy is going to be chlorine, because it's closer to that upper right-hand corner. It's going to be really hard to pry an electron away from chlorine. It's got 7 valence electrons. And then which group belongs to 5A? And we know that 5 can be directly related to how many valence electrons it has. So which of these has 5 valence electrons? And that would be nitrogen. So that could be an example of how you're using these properties. And that's it. Okay, so we actually are going to finish up early today. That should get you through your homework assignment and your labs for the weekend. Yeah, so you're all good. If you have any questions, feel free to stay around and I can help you out. Enjoy your weekend, stay dry, stay safe. I think there's supposed to be some ice storms maybe coming. We had such a nice day the other day. I'm going to use that day to get me through the next week or two, and then maybe we'll get another nice day in there. So enjoy your weekend. It was nice to see you all. Bye-bye.